Thank you again for joining us on this webinar about Echoview 11. My name is Briony and I'm here to show you through the new features in our very latest version of Echoview. Echoview 11 was released in late April 2020 and it includes a great collection of new features that we'll work through during this webinar. The highlights of this release are the Calibration Assistant, live viewing additions, distance mode options for school detection, improvements to our performance, CTD profiling options, and some other tools and customization options to make your use of Echoview more effective. We'll start with the Calibration Assistant, which it appears many people are really interested in, which is very exciting for us. So the Calibration Assistant is a new tool in Echoview that helps you to calculate calibration parameters. And as we know, the goal of calibration is to ensure reliable and quantitative echosounder measurements. We want our measurements to be as accurate and as consistent over time and space and across instruments as possible so that our numbers are comparable. Echoview allows us to calculate correction factors for TS, which is sometimes referred to as SP, and also SV. And we can calculate our beam pattern characteristics so that we can accurately beam compensate our targets. Echoview 11, the calibration tool, is compatible with any narrowband data file format that Echoview supports, so single, split, or dual beam echosounder systems. And the assistant is licensed with the Echoview Essentials module. And before I continue, I just want to highlight that this webinar won't be an in-depth tutorial on general calibration concepts or theory, but rather it's an introduction to Echoview's new tool that supports this important step for hydroacoustic data processing. Some of the benefits of using Echoview to perform your calibration. One of the advantages that we see is that it provides great flexibility. For example, the fact that we support multiple systems, multiple hardware. It also gives you complete control over your data, so the targets that are used and the SV samples that are integrated. And we can do data quality control measures, such as removing noise. We can also easily perform sensitivity analyses so that we can understand the implications of decisions that you make in the calibration process. And finally, our algorithms are fully documented in our help file. The Calibration Assistant allows you to calculate SA correction and transducer gain if you're working with a SIMRAD system, or SV and TS offsets for data from other manufacturers. And we can also calculate our minor and major axis angle offsets, our minor and major 3 dB beam angles, and our RMS error for use in beam compensation. The philosophy behind the Calibration Assistant is that it's been independently developed and implemented, and our calculations are identical to those in the IC's Cooperative Research Report number 326, the calibration of acoustic instruments, where possible. And for calculations that were not defined in the research report, which includes the angle offsets and 3 dB beam angles that are used in beam compensation, and also defining the integration envelope for SV, we are providing algorithm details in our help file. The Calibration Assistant has undergone very extensive and thorough testing by multiple staff to ensure that our calculations are as we expect them to be. And we've performed our calculations using Python, RCode, and other in-house tools that we've been working on in-house. We've also run some comparisons to ESP3 and SIMRAD software and their calculation outputs. So let's take a look at the Calibration Assistant with a demonstration. I shall start up Echoview 11. And to acknowledge the source of this data, Harris Knath, on behalf of the CSIRO, shared this data with us. It's data that contains measurements of a 38.1 millimeter tungsten carbide calibration sphere that was collected using a SIMRAD EK60 at 2 frequencies, 38 and 120 kilohertz, and with a calibration sphere in about 17 meters of water from last year. I'll create a new EV file, and in my file sets window, I'll add a data file. In my data flow window, I'm just going to right-click arrange objects, just to arrange our objects based on transducer neatly. For this demonstration, I'm just going to look at one of the frequencies, the 38 kilohertz. So let's take a look at the TS data. You can see we've got about 17 meters of range here. We've got our calibration sphere below some level of noise as we scroll through the data. Or I can close my filesets window and use zoom to extents just to show the length of this particular example data set. I'm just going to adjust my color scheme to -100 minimum and display range of 100, just to take a good look at this data. Now, the first step in calibration is to account for our environmental and data collection settings. This is done in Echoview, as it has been for some time now, using an ECS file, which we can add in our filesets window. I've prepared one previously that I'll apply. I won't go into the details of what's in that, but important to make sure we use that. I'll also create 2 lines for analysis so that we can just focus really on the sphere data. In my data flow window, I'm just going to create 2 new lines, virtual lines. It could be any type. I'll use a fixed depth for above sphere, and I'll set that to 11 meters. And I'll repeat the process, new virtual line, fixed depth for below sphere at 13 meters. And we can see these 2 lines are now visible on the echogram. I'll also create a single target detection variable. Right click, new variable. I'll type single to filter, and I can find my single target detection split beam method 2 because I'm working with split beam data from EK60. Press OK. I'll just stick with the default settings for now. Press OK. And I'll view my echogram. So now we're looking at our raw TS data and our detected targets, and we just need to filter this data a little more. We can do that by opening our variable properties. First thing we'd like to do is simply remove the targets that are above the 2 lines that we defined previously. When I apply that, our targets have gone. Also, I will define a lower TS threshold of -52.4 dB. This is 10 dB lower than the expected TS of the sphere that we were working with. I'll reduce my minimum normalized pulse length to 0.2, and I'll increase my maximum beam compensation to 6. And these are the only settings I'm going to change for this example. You can see our targets. And now what you might have noticed with this data, if I zoom out a little bit, is there's a little bit of noise, and we want to make sure that we don't include this when we're calculating our calibration parameters, so we can exclude that data. I'm going to use the vertical band tool and define some regions based on what I'm eyeballing in the TS variable. So I'll click and drag, right click, define region, and I'll set that region to bad data so that it's all of the data that's underneath these regions will be excluded from further analysis. We'll just do a few more regions where we might be a little doubtful about the quality of the data due to other noise. Quite easy to do, but we can also, if we prefer, zoom in on our single target echogram and just check our targets, and if there were a target we wanted to remove, we could just draw a smaller region as well. Okay, so I've defined my bad data regions. What I would also like to do is I'm just going to define my analysis region for the targets. I'll use the horizontal band selection tool, click and drag just roughly in the area of our targets, right click, define region, and this one will be an analysis data type, analysis region type. So that's good. We're all pretty set up. First thing we can do now is just take a look at the data in some graphs. Firstly, I'll graph our angles. This is essentially our top-down view of our data. And in this particular case, we can see we've got really good coverage across the beam, so it's a pretty good start for our calibration. And then we'll take a look at the new graphs in Echoview 11. There's 3. So graph region, off-axis beam compensation, graph region, minor axis beam compensation, graph region, major axis beam compensation. So these are our 3 new graphs. Let's just arrange this a little bit better. And what we can see here is we've got compensated targets in blue and uncompensated targets in the orange. And ahead of actually calculating our official calibration parameters, it's good to look at this data, and we'd expect to see a nice relatively flat response for the compensated targets. And we'd expect to see a fairly curved response for the uncompensated targets. And this is showing the effect of the beam pattern on the target strength. So that looks pretty good. We'll move on to using the Calibration Assistant. I'll close these graphs. So the Calibration Assistant, we can launch this 3 different ways, just like we can for our graphs. Either by selecting a region and using the Calibration Assistant for a region, or we could make a small selection on the echogram, start the Calibration Assistant for that selection, or the third way is to go to the echogram menu and use the Calibration Assistant on the entire echogram. I'll launch it for the region, and we've opened up our Calibration Assistant now. So the first step that we need to do is to enter our expected target strength of the sphere at this frequency in these conditions, which in this case is minus 42.4. And then we want to check the other things that we've got set up here. Firstly, the SV variable that we're going to integrate should be the SV variable from the same transducer that we're working with our targets from. We can choose how we want to integrate our samples. I'll stick with the default of transmitted pulse length. We need to define what we consider on-axis targets. I'm going to stick again to my default of 0.5 degrees, so anything beyond 0.5 degrees off-axis won't be included. And because we're working with SIMRAD data, we're using the SIMRAD lobe beam compensation model, and we're using SIMRAD-specific outputs. Alternatively, we can use generic outputs, but we want SIMRAD in this case. Now that we've identified our on-axis definition, we can click on our second tab up here, Target Summary, and we get some basic coverage of what we're looking at with our data. So I've started with more than 4,000 targets, which have been reduced down to 100 due to my on-axis targets definition. And we get our average target strength uncompensated, our angles, and the minimum and mean. So it's a quality assurance check here. And so this is all good. We can click Calculate down the bottom and get our results. It's that easy. So what we're looking at now is our right-hand side of this window. We've got 2 columns, current and new. Current are the values that have either been read from the data file or overwritten due to values in the ECS file. So that's what's being used currently. And then new is what we're calculating as a result of the calibration process. So these are the values you would then go on and apply for your survey. So that's it. It's quite simple. And I guess this is also a good point at which to talk about where we're going to take this in the future. In the future, we'll extend it so that we can calculate this during live viewing. We're going to incorporate more graphs into the assistant itself. We'd like to extend it so that we can do wideband calibration as well as narrowband. And hand in hand with that, we'll be implementing our built-in standard sphere TS calculations. So currently we have to enter it in manually. for example, using the NOAA calculator for standard sphere. But in the future, we're planning to build this into Echoview itself. And finally, lots more learning resources for this really important part of the hydroacoustic data processing, expanding on what we've already added to the help file, and also creating tutorial and training materials on this topic. In the help file itself, there's two really key pages. So with the Assistant open, you can press the Help button to jump straight to one of them, which is the Calibration Assistant dialog box page. I recommend having a good read of this. And then secondly, the Calibrating an Echosounder page. This is where the algorithm details can be found, as well as links to the NOAA standard sphere calculator. Finally, I've got to mention in Echoview itself, Calibration Assistant settings are stored per single target detection variable. So these parameters will be remembered. If you want to try different parameters or compare across frequencies, of course, then you can create new single target detection variables and store their sets of parameters independently. Moving along to live viewing in Echoview. Live viewing is a module that you can purchase on a license, a standalone license. And this module enables you to perform real-time viewing of data as it's being recorded by an echosounder or a sonar. So in real time, we can view echograms, cruise tracks, graphs. We can apply templates to make our data processing more efficient with pre-saved settings. And we can create 3D curtains, lines, and regions, all within moments of the data being recorded by the echosounder. This is done by way of a utility program called Echolog, shown on screen. And this data will monitor the folder where your echosounder is writing the data files. It will monitor, collect the data, and then broadcast it to Echoview. Echoview and Echolog can run on the same computer, or they can run on different computers on the same network. And multiple copies of Echoview can listen to the data that's being broadcast by one copy of Echolog. Using live viewing allows you to explore data with a lot more control than the echosounder software can offer. It means you can zoom easily, change colors, scroll backwards and forwards in time. And you can really take the opportunity to monitor the quality of data while it is being collected. Live viewing allows you to detect and calculate early results, and also provides you with better insights during calibration. You can output processed data in real time, and you can also output a logbook of observations after a survey. The types of echosounders that are compatible with Echoview, we've had support for Simrad, EK500, EK60, EK80 family of systems for quite a few years now, including wideband and the EK80. But in Echoview 11, we added support for biosonics echosounders, soundmetrics, imaging sonars, and a Kongsberg sonar. We can also add support for more echosounders or sonars on request, so please let us know if there's a type of data you would like to view in real time. And I'll give you a quick demonstration with some Simrad EK60 data as to how useful this tool can be. And the demonstration will be based on the paper that I'm showing on screen, Jack and Michael's. So I shall open Echoview, close this file. I'm just going to simulate using an echosounder here, using one of our tools as I'm sitting in a place not on a ship. So I'll start the simulator, which you can't see, and then I'll also start Echolog. I've set this up to monitor a folder for new data that's being recorded, and we can see Echolog is reading files. So that's good, that's the first step. And now in Echoview, in our live viewing window towards the bottom is where I've got it set up. You can show or hide that little box if you need. We can see that it's detected that there's an Echolog working, and if I double click this, it'll start. I've set this live viewing template up, and what we can see is raw variables for 5 frequencies on the right-hand side, 18 kilohertz through to 200 kilohertz. And on the left, we can see, firstly, our data flow window that has quite a number of steps for each frequency set up. These steps remove noise and otherwise manipulate the data. And I won't go through the details of this particular technique. It's available in the paper, and you can also contact us for help with it. But the end result is shown in this bottom left window, where sample data has effectively been recolored to represent frequency response. So whether the backscatter was strong or weak in one or more frequencies. We are also using a custom color scheme to help with that visual tool. It's a clever technique, and without necessarily understanding the details, hopefully we can see that this is quite a useful visualization technique during a survey. That's live viewing. Distance mode options for school detection. Echoview 11 includes new options for the settings that define school detection when you're working with single split or dual beam data. School detection is an algorithm that you can use to delineate aggregations of fish, zooplankton, bubbles, or other targets. And until Echoview 11, GPS or vessel logs were required to define the minimum candidate and school lengths and maximum linking distances. In Echoview 11, we're now able to also use ping number and ping time. This means that fish schools, gas plumes, or other aggregations can easily be detected, even if GPS positions were not recorded, or for data collected from a mooring or another fixed platform. I'll give you a demonstration of this quickly in Echoview. I can close my file. This example data, we're looking at some ASL environmental AZFP data that's kindly shared by David Lemon from the ASL company. And this is AZFP data that was collected from a drifting surface buoy and shows a layer of euphorsids that are migrating to the surface. In this EV file, I've pre-prepared a couple of steps. So I've detected the bottom because we want to exclude data below that. I've set up a surface exclusion line as well. I've used the background noise removal to reduce the noise that we see increasing with range. And then I've also used an X by Y convolution just to smooth the data to make outlines a bit easier to draw, to delineate. Finally, I applied a data threshold of -80 dB to use in our detection. So in our EV file properties dialog on the schools page, this is where we set up our algorithm for schools detection. So Echoview 10 and older only had GPS distance and vessel log distance, but now we also have the ability to define ping number or ping time. I'm going to use ping number, look for schools that are at least 100 pings long, 2 meters high. Press OK. So that's set up. Now for my echogram, I'll just go to the echogram menu and click Detect Schools. This gives us a few options. Importantly, also a nice little shortcut to that dialog that we were looking at, where we can define our algorithm settings. That's set up how I want it. So I'm going to click Detect. And this algorithm will run. And we can see we've now identified a boundary around this layer of euphorsids as they're migrating, which we can then use in further analysis of our region. So quite handy in the cases when you don't have GPS data necessarily. Or if you just prefer, if you can use this too if you have GPS data but would just simply prefer to identify by ping number or time. Next up, performance improvements. So this is really exciting. Echoview has a major boost in performance across many processor and time-intensive aspects of our software. And this improvement applies to all data types and applications. For most situations that we've tested, which has been quite a lot, Echoview 11 is 3 or 4 times faster than Echoview 10. And in some situations, Echoview 11 is more than 10 times faster. I'll give a quick demonstration of this. Close this file, and I'll just set Echoview 11 to one side. And I'll also open Echoview 10. All right, Echoview 10 on the left. And so I've created 2 EV files. Well, I've created one EV file that I've copied, so the 2 files are identical, called performance demo. And I'm going to open both of these at the same time, and we can just compare Echoview 10 and Echoview 11's performance. So Echoview 10, Echoview 11, and the first few pings open up fairly quickly in both cases, but what's the crucial difference is if I click in this window and then zoom to extents, in other words, I'm calculating all of my data, this is where we'll see the difference. And so thanks to Tim Ryan from CSIRO for this data. This was a key data set for our testing. The full data set and workflow that was being used here took originally approximately 22 hours, and we've got that down to 2 hours. And you can see on the right here, Echoview 11's finished, Echoview 10 is still thinking very hard. In this particular example, I've got a subset of just 5 hours of data, 14,000 pings or so, and a workflow that wasn't very well optimized prior to Echoview 11. We're still thinking. So the improvements that we've got in Echoview 11 are a result of increased multi-threading. So we're maximizing our CPUs and using those. We've also improved how we use computer memory and just the efficiency of data flowing through virtual variables. Our performance adjustments are really quite dependent on the actual computer that you're working with yourself. So we recommend having 16 gigabytes of more of RAM, a really good CPU, and data stored in a fast access location such as a local SSD. Echoview 10 is still thinking away. Quite a good example. We've got quite a lot of information. There we go. It's happened. We've got quite a lot of information in our help file about computer specifications, and we're also happy to provide advice if you're buying a new computer and want to get something that will work well for a good period of time. Next, taking a look at CTD profiling. Echoview 11 contains our first steps towards full correction of data for CTD measurements. In Echoview 11, we have two new calibration settings, CTD depth profile and sound speed profile, that can be used for any narrowband EK80 and EK60 data. We use these settings to provide an array of values, and this can be at any resolution that you like. It's just important that you have the same number of entries in these two arrays. Once these values are read, the range for each sample is adjusted based on sound speed. Part of this means that sample thickness of each sample changes as a result of differing sound speeds. So Echoview will then run some background resampling to transform potentially irregular samples back onto a regular grid. We'll take a quick look at how this works in Echoview. Close this file, and I'll just make a new file. We'll just use this data that we were looking at previously. So I'll first set up a 1 meter grid. This is quite shallow data, so 1 meter. And then what I'm going to do is create an ECS file that shows how to use these settings. So new CTD. So this has just created a default ECS file. And for my SVT1 data, I'm going to add the new settings. So firstly, CTD depth profile. And I'll use just a simple example, 0, 5, 10, 15 meters. And then sound speed profile. And a fairly artificial example, 1500, 1490, 1480, 1470. Now, if I move this over a little bit, if we watch the echogram and how it shifts when I save this file and Echoview updates the calibration that it's read, file save, we can see our echogram has shifted a little bit as a result of the adjusted range from this profile. This is our first step in this space. And the next steps are to expand how we're using these sound speed values. So the corrections will be used in calculations for the range term, in TVG range correction calculations, in our SV volume term, and also feeding through into other tools such as bottom classification and the Calibration Assistant. And once we've locked that all down for sound speed, we'll then extend it for absorption coefficient so that you can have a profile of absorption coefficient values. We'll use other file formats, and we'll see if we can have it vary by time or location as well. Next, some quick tools that make life a little bit more fun when you're working with Echoview. Firstly, we'll look at improved lists. So I'll just create a copy variable in this file. Often if we're working with complex data file, EV files, we might have a lot of variables. So when we're making a new variable, it can be a bit painful to try and find our variable in this list. So as well as it being sorted, we now also allow filtering. So if I type SV, we can see Echoview's filtered down just to the two variables with SV in the name. Or we could do T1 to find all the variables from that transducer. So just using the keywords. I use that for operand input, but there are other places that you can find this filtering now, such as our analysis lines. We can filter by typing here too. Just a small little time saver. Another is the ability to customize the appearance of our grid lines and our labels. For this variable properties, on the grid page, we've now got these new settings for custom grid display. If I click custom, make it a bit thicker, a few more pixels, change the color, press apply, we can see that's reflected on the echogram. That's a fairly awful color choice that I've chosen there, but it gives you the capabilities now to make these things more visible if you're capturing the screen for presentations or other use. Likewise, we can also make our labels bigger too, so that they're more visible. In our color legend, you'll see we've now got units that are displayed. In a label, we can choose whether we show this on the left or the right, or we can also turn it off. Again, this is useful context if we're capturing the screen to use in presentations or other places. And then I'll finally wrap up with some pretty visuals. So this paper was recently published and explores how color maps can influence what we're looking at with fisheries acoustics data, published in the ICES Journal of Marine Science this year. And the authors used, this image is from the paper, and the authors demonstrated using an image of Tony Blair how different color maps can influence our perception. In this image, popular color schemes that are used by various hydroacoustic systems are compared to other color maps that may be better when you're visualizing data. We've added support for the Viridis color scheme in Echoview, and some variants of this. And as demonstrated by Milne Technologies, who is a consulting company from Canada, if you start using these new color schemes, you might find all sorts of interesting features in your echograms. So be careful what you choose. But more seriously, we've added Inferno, Magma, Plasma, and Viridis based on MATLAB library color maps for better visualization of continuous scalar data in Echoview 11. And these color schemes are available by right-clicking in the color legend on the echogram window or through the variable properties dialog. So in Echoview, we can just right-click color scheme. We can see the color schemes that are available and easily change it, or we can open variable properties. And on our echogram display page, we can also find the list here and change it. There are other new features in Echoview, lots of really cool stuff, and with every release I always encourage people to read this key page in our help file, which we update with every release, which is what's new in the latest version in great detail and with links to further information. Reading through this means that you can make sure you know what's out there, you know what we've added, and you can use Echoview more effectively. And if you have any questions about any new features, please contact us, support@echoview.com, as we're happy to help you to understand if it's not clear. When you upgrade to a new version, we recommend regularly checking for new updates via the Help menu, Check for Updates option. And Echoview will tell you if there have been any releases since the original release. So in this case, when I took the screenshot, we've had 2 updates to Echoview 11 since we first released it, mostly with some minor bug fixes, but also some new changes as well. And so it's worth looking to see what has changed since initial release. So thank you very much for attending this webinar. If you have any feedback, please send through and let us know. We really value your feedback for deciding what we do in future versions of Echoview. And I also wanted to mention that tomorrow is 25th anniversary of Echoview Software as a company, which is really exciting and quite a long time for a software company. We're very proud of that. So we'll be sharing more information through our channels about this 25th anniversary soon.